Welcome to the Whispering Galaxy, where we explore the deepest mysteries of our universe through gentle contemplation and quiet wonder. Tonight, we're embarking on a journey that might just change how you see everything around you. Before we begin, I'd love to know where you're joining me from tonight. Are you nestled in a comfortable chair with the evening light fading outside your window? Perhaps you're lying in bed, ready to let your mind wander through the cosmos. Wherever you find yourself, I hope you'll settle into one of the most beautiful and ready to drift and bewildering realms of science. If you find these cosmic explorations soothing and thought-provoking, a gentle tap on the like button helps this little corner of the universe grow. And to those of you who've already joined Wanderers, thank of Cosmic our community you. Your presence here means more than you might imagine. Now, I should warn you that tonight's topic might be so fascinating that it keeps you awake longer than intended. But if that happens, at least you'll drift off with a deeper appreciation for just how extraordinary the reality beneath our everyday world truly is. So let's begin this gentle voyage into quantum physics, shall we? What if I told you that the solid chair you're sitting in is mostly empty space? That the atoms making up your body are buzzing with activity you can't feel, engaged in a dance so intricate and mysterious that Aven's the worldest minds are still trying to understand it? What if the very act of looking at something could change its behavior, as though the universe itself were shy and transformed whenever it felt your attention? Science fiction, or... This isn't mystical thinking. This is quantum physics, the branch of science that describes the behavior of matter and energy at the smallest possible scales. And it reveals a world so different from our everyday experience that it almost feels like stepping into a dream where the usual rules simply don't apply. For most of human history, we've understood the world through our senses and the tools that extend them. We see objects with clear boundaries. We feel solid surfaces. We watch things move from one place to another in predictable ways. A ball thrown into the air follows a path we can trace. A coin flipped will land either heads or tails. The moon hangs in the sky whether we're looking at it or not. But as scientists began peering deeper into the structure of matter during the late 19th and early 20th centuries, they discovered something remarkable: the stranger. The deeper they looked found a realm things became. They where particles could be in multiple places simultaneously, alter reality, where the simple act of observation could fundament, and where certainty gave everything they thought they knew about how way to probability in ways that challenge the universe works. The story begins with light, that familiar companion that illuminates our days and guides our nights. For centuries, scientists debated whether light was made of particles or waves. It seemed like such a simple question, the kind that should have a clear, definitive answer. Waves behave in particular ways, creating patterns when they interfere with each other, bending around obstacles, spreading out as they travel. Particles behave differently, following straight paths, bouncing off surfaces, maintaining their individual identity as they move through space. But light refused to fit neatly into either category. In some experiments, it acted like a wave, creating the interference patterns that waves are known for. In others, it behaved like a stream of tiny particles, each carrying a discrete amount of energy. This wasn't a matter of experimental error or inadequate tools. Light genuinely seemed to be both things at once, or perhaps neither, depending on how you looked at it. This discovery was just the beginning. As researchers delved deeper into the atomic world, they found that this strange dual nature wasn't unique to light. Electrons, those tiny components of atoms that we often imagine as little balls orbiting a nucleus, also displayed this mysterious behavior. Sometimes they acted like particles, sometimes like waves. The very foundations of classical physics began to crumble under the weight of these observations. Imagine trying to describe the location of an electron around an atom. In the classical world, this should be straightforward. The electron should be somewhere specific at any given moment, just like a planet orbiting the sun. But quantum physics revealed something far more peculiar. Rather than occupying a definite position, electrons exist in what scientists call probability clouds. These aren't physical clouds made of water vapor or dust. They're mathematical descriptions of where an electron might be found if you were to look for it. Think of it this way. If you were blindfolded and asked to describe the location of a friend who was quietly moving around a room, you might say there's a high probability they're near the comfortable chair, a moderate chance they're by the bookshelf, and a small possibility they're standing by the door. But until you remove the blindfold and actually look, your friend exists in all those locations simultaneously, at least in terms of your knowledge of their position. Electrons around atoms exist in a similar state of uncertainty, but with a crucial difference. It's not just that we don't know where they are. They genuinely don't have a definite location until the moment we measure them. They exist in what's called a superposition of all possible positions, a ghostly blend of every place they could be. This concept of superposition extends far beyond the location of particles. An electron's spin, its energy level, its momentum, all these properties can exist in superposition until the moment they're observed. It's as though nature keeps all options open until forced to make a choice, and that choice only happens when we peek behind the curtain. But here's where things become even more intriguing. The act of measurement doesn't just reveal a pre-existing reality, it appears to create that reality. Before you measure an electron's spin, it's not secretly spinning in one direction or another while you're unaware. It's genuinely spinning in all possible directions simultaneously. The measurement forces it to choose a specific direction, collapsing all those possibilities into a single outcome. This idea troubled many early quantum physicists, including Albert Einstein, who famously declared that he couldn't believe the universe was fundamentally governed by chance and uncertainty. He felt there must be hidden variables, some deeper layer of reality that determined outcomes in advance, even if we couldn't access that information. But decades of increasingly sophisticated experiments have consistently supported the quantum view. The universe really does seem to operate on probability rather than certainty at its most fundamental level. Consider what this means for our understanding of reality. Every atom in your body, every photon of light reaching your eyes, every interaction between particles in the world around you operates according to these quantum principles. The solid, predictable world we experience is built upon a foundation of uncertainty and possibility. It's like discovering that A is constructed not magnificent cathedral from stone blocks, but from probability clouds that somehow maintain their shape and strength through the collective behavior of countless quantum interactions. This quantum realm operates by rules so different from our everyday experience that even the language we use to describe it feels inadequate. We speak of particles and waves because these are concepts we understand from our macroscopic world. But quantum entities are neither particles nor waves in any conventional sense. They're something else entirely, something that exhibits properties of both depending on the circumstances and how we choose to observe them. The implications ripple outward from the microscopic world into our daily lives in ways both subtle and profound. The electronic devices that surround us, from the smartphone in your pocket to the computer that might be playing this video, all depend on our understanding and manipulation of quantum effects. The GPS system that helps navigate our travels relies on quantum mechanics to maintain its precision. Even the process of photosynthesis, by which plants convert sunlight into chemical energy, appears to harness quantum effects to achieve remarkable efficiency. Yet despite these practical applications, quantum physics remains deeply mysterious. We can calculate probabilities with extraordinary precision, predict the statistical behavior of quantum systems, and build technologies that exploit quantum effects. But the fundamental questions about what it all means, about the nature of reality itself, remain as puzzling today as they were a century ago when these discoveries first emerged. As we prepare to delve deeper into this quantum landscape in the episodes that follow, remember that you're not expected to understand everything immediately. Even the physicists who work with these concepts daily will admit that quantum mechanics doesn't feel intuitive. It challenges our basic assumptions about how the world works, asking us to accept that reality might be far stranger and more beautiful than we ever imagined. Tonight, we've opened the door to a realm where certainty gives way to possibility, where observation shapes reality, and where the very small reveals truths about the very large. In our next exploration, we'll venture further into this quantum wonderland, discovering how these mysterious principles give rise to the stable, predictable world we know and love. So rest easy tonight, knowing that beneath the familiar surface of things lies an ocean of mystery and wonder, a whispering galaxy of possibilities that continues to unfold its secrets to those patient enough to listen. Let me journey deeper into this on a gentle or discover how nature's smallest quantum realm, where we secrets weave together to create the tapestry of existence we call. Picture home yourself standing in a garden at twilight, watching the last rays of sunlight filter through the leaves. That golden light carries with it one of the most profound mysteries in all of science. Each beam consists tiny messengers call of countless puzzles that these photons embody add photons, and riddle that greatest minds of the early 20th century first began studying how objects glow when heated. They expected to find simple, predict up a piece of metal, and it should emit light in a smooth, continuous spectrum. But nature had other plans. The mathematicists came describing this process led to an impossible conclusion to call the what physics-violet catastrophe. According to classical physics, heated objects should emit infinite amounts of energy at high frequencies, which was clearly absurd. This crisis in understanding led a German physicist named Max Planck to propose something revolutionary. What if energy didn't flow smoothly like water from when scientists tap, but instead cameable patterns, heat in tiny, indivisible packets? He called these packets quanta, from the Latin word meaning how much. It was a desperate mathematical fix, something Planck himself didn't fully believe. He thought future scientists would find a better explanation that wouldn't require such strange assumptions. But Planck's quantum hypothesis turned out to be far more than a mathematical convenience. It was the first glimpse into a fundamental truth about reality. Energy, it seemed, comes in discrete chunks, like coins that cannot be divided. This discovery would eventually reshape our entire understanding of the universe. Albert Einstein, recognizing the profound implications of Planck's work, extended this quantum thinking to light itself. He proposed that light consists of individual particles of energy, what we now call photons. Each photon carries a specific amount of energy determined by the frequency of the light. This explained a puzzling phenomenon called the photoelectric effect, where light striking metal surfaces could knock electrons loose, but only if the light had a high enough frequency. It didn't matter how bright the light was, only its color, its frequency, mattered for ejecting electrons. Einstein's photon theory revealed that light has a dual personality. Sometimes it behaves like a wave, spreading and interfering with itself in the familiar patterns we observe. Other times, it carrying its acts like a stream of particles, each photo of energy. This wave-discrete packet, one of the corner particle duality, became challenging our intuitive understanding of what-stone mysteries of quantum physics. The strangeness was things can be, but only beginning. As physicists probed deeper into atomic structure, they discovered that this dual nature wasn't limited to light. Electrons, protons, neutrons, indeed all the fundamental constituents of matter exhibited the same bewildering behavior. They could act like waves or particles depending on how you observed them. This led to one of the most famous experiments in the history of science, elegant in its simplicity, yet profound in its implications. Imagine shining light through two narrow slits cut into a barrier, then observing the pattern that emerges on a screen behind the slits. When both slits are open, you might expect to see two bright lines corresponding to light passing through each of alternating bright and dark bands opening. Instead, you see a series, an interference pattern that can only be explained if light behaves like a wave passing through both slits simultaneously. The mystery deepens when you reduce the intensity of light until only one photon at a time passes through the apparatus. Logic suggests that each individual photon must go through either the left slit or the right slit, but cannot possibly go through both. Yet when you collect enough individual photon impacts, they still form the same interference pattern. Each photon somehow interferes with itself, as though it travels through both slits at once and meets itself on the other side. The plot thickens when you place detectors at the slits to determine which path each photon actually takes. The moment you do this, the interference pattern vanishes. The photons begin behaving like ordinary particles, each going through one slit or the other, creating two simple bands of light on the screen. It's as though the very act of observation changes the fundamental nature of reality. This isn't of our instruments or a quirk of light. The same behavior appears when the experiment is performed with electrons, atoms, even large molecules. The universe seems to exist in a state of potential until the moment we look, at which point it crystallizes into definite reality. These discoveries force scientists to develop an entirely new mathematical framework for describing the quantum world. At the heart of this framework lies something called the wave function, a mathematical entity that encodes all possible information about a quantum system. The US where wave function doesn't tell a particle is or what it's doing. Instead, it tells us the probabilities of finding the particle in various states when we choose to observe it. Think of the wave function as a ghostly map of possibilities. For an electron around an atom, this where the electron is map shows regions likely to be found, like a probability landscape with hills and valleys. The electron doesn't orbit the nucleus like a tiny planet as we once imagined. Instead, it exists as a cloud of possibility, simultaneously present in all allowed locations until the moment we measure its position. This probabilistic nature extends to every property of quantum particles. An electron's spin, its energy, Xi states of its momentum, all exist in fuse superposition until measured. It's not that we don't know these properties. They genuinely don't have definite values until the act of measurement forces them to choose. Werner Heisenberg formalized this uncertainty into a fundamental his name. The principle that bears uncertainty principle states that certain pairs of properties cannot be measured simultaneously with perfect precision. The more accurately you determine a particle's position, the less precisely you can know its momentum, to limitation of our measuring and vice versa. This isn't instruments. It's woven into the very fabric of reality. At first glance, this might seem like a problem, a flaw in the universe's design. But uncertainty turns out to be essential for could be pin the stability of matter itself, a kind of quantum. If electrons dematter, as we know it, couldn't exist. The uncertainty principle provides positions and momenta, veined down to exact, would spiral into atomic nuclei. An, in the classical uzziness, also enables pressure that keeps atoms whirled if you don't have one of nature enough energy to climb over stable and chemistry possible. This quantum F's most remarkable phenomena, quantum tunneling a wall you simply can the other side. But in the quantum get-to realm, particles can tunnel through barriers that should be beyond classical boundaries, giving particles a small probability of appearing on the other side of obstacles they shouldn't be able to cross. Tunneling might sound like exotic physics with no practical relevance, but it powers the stars. Nuclear fusion and repulsion between atomic on quantum tunneling to overcome the electrical stellar cores relies nuclei. Without this quantum effect, the nuclear furnaces that light could in the cosmos it igen and the universe quantum principles would be levels of atoms, it, energy also explain the a cold, dark place. These discrete Y electrons occupy specific orbital shells rather than continuous ranges of distances from the nucleus. The electron's wave nature creates standing wave patterns around the atomic core, and only certain the familiar world of to see that, as we contemplate these quantum mysteries, we begin chemical composition of distant stars. Astronomers to identify thermal lines that allow gives rise to the spect. This quantization of energy level 6 of a musical instrument, properly, like the Harman wavelengths fit, our senses, emerges from an underlying realm of pure you, the air possibility, the solid chair supporting between probability clouds that somehow maintain enough you breathe, the light illuminating your sorrow, the stable patterns we experience as physical reality. The quantum world operates by to our everyday experience that even sees coherence to create undings, all arise from quantum interactions. Ists admit logic so foreign to finding on physic deeply realm, underlies everything counterintuitive. Yet this strange we know and love about the universe. Every chemical bond, every biological process, every technological collapsing into classical marvel depends on the delicate dance of quantum possibilities reality. In our next gentle exploration, we'll discover how these quantum principles give rise to one-wave function, extends slightly to be impenetrable, the end, the ordinary, how these quantum connections might weave together the very fabric of reality itself. For now, rest in the knowledge that you boundaries of space and time will see entanglement, where particles become connected in ways that transcend the most mysterious phenomena in physics worlds. The classical possibility and gentle and predictable mote exist at the intersection of two eons, and the quantum realm of infinite realm of defin real, equally important and equally white objects uncertainty. Both are equally ondrous in their own mysterious ways. Sleep begins to weave its gentle spell as we drift deeper into quantum territory, where the familiar boundaries of space and time start to soften and bend. Tonight, we'll explore one of the most ench of quantum physics, anting and bewildering aspects, a phenomenon so extraordinary that it troubled even Einstein himself. He called it spooky action at a distance, though today we know it by a name, quantum entanglement. More elegant a moment that you have. Imagine for a pair of coins, not ordinary coins, but magical ones that remain forever connected, no matter how far apart you take them. When you flip one and it lands heads, the other instantly becomes tails, even if it's on the other side of the galaxy. This instantaneous connection doesn't rely on any signal traveling between them. There's no hidden communication, no secret message racing through space. The coins simply know about each other's state in a way that defies our everyday understanding of is the how the world works. This essence of quantum entanglement, though the reality is far more subtle and beautiful than any analogy can capture. When two particles become entangled, their quantum states become intertwined in such a fundamental way that measuring determines one immediately the state of the other, regardless of the distance separating them. They form a single quantum system, a unified whole that transcends the classical notion of separate objects existing independently in space. The process of creating entangled particles is surprisingly straightforward. When certain types of particles interact, or when a single particle splits into two, they can become quantum mechanically linked. Perhaps two photons are created from the decay of a single atom, or two electrons interact briefly before flying apart. In that moment of connection, something lose profound happens. The particles, their individual identities, and become part of a larger quantum entity that encompasses both of them. What makes this so remarkable is that before measurement, neither particle has definite properties. An entangled photon doesn't have a predetermined polarization direction, and an entangled electron doesn't have a fix. Instead, both spin orientation particles exist in superposition states, embodying all possible values simultaneously. But these superpositions are correlated. If one particle is measured and found to have a particular property, its entangled partner instantly manifests the corresponding complementary property. The speed of this connection appears to be instantaneous, faster than light itself. This troubled Einstein because it seemed to violate the cosmic speed limit established by his theory of relativity. Nothing, not even information, should be able to travel faster than light. Yet entangled particles appear to communicate their states instantly across any distance. Einstein, along with colleagues Boris Podolsky and Nathan Rosen, argued that this apparent faster-than-light connection must be an illusion. They proposed that the particles must carry hidden information that determines their behavior in advance, like secret instructions tucked away in their quantum pockets. For decades, this remained a philosophical debate, rather than a scientific question that could be definitively resolved. But in the 1960s, physicist John Bell developed a mathematical test that could distinguish between Einstein's hidden variable theory and the predictions of quantum mechanics. When scientists finally performed these experiments, the results were clear and consistent. Quantum mechanics was right. The particles really do influence each other instantaneously, and there are no hidden variables determining advance. This doesn't mean you can use entanglement to send outcomes of quantum measurements faster than light. They are fundamentally random, so what result you'll get when you can't control you measure your particle. Even though the entangled partner responds instantly, the correlation only becomes apparent when both parties compare their results through conventional, slower-than-light communication. The universe maintains its causal structure while still allowing for these mysterious quantum connections. The implications of entanglement extend far beyond laboratory curiosities. Some physicists now believe that entanglement might be the fundamental fabric from which space and time themselves emerge. Rather than thinking of particles as separate entities connected by entanglement, we might need to envision reality as a vast network of quantum correlations, with what we perceive as individual objects being merely different aspects of this underlying unity. This perspective suggests that the classical world of separate objects interacting through forces might be something like reality. At the deepest level, everything an optical illusion, a consequence of our limited ability to perceive the full quantum, might be interconnected in ways that transcend our ordinary concepts of space and time. The electron in your body and a photon from a distant star might share quantum correlations that link them in ways we're only beginning to understand. Modern technology has begun to harness these quantum connections. Inography uses entangled particles to create remarkable ways. Quantum crypt perfectly secure communication channels. If anyone tries to intercept the quantum encrypted message, the act of measurement disturbs the entanglement and reveals the eavesdropping attempt. Quantum computers rely on entanglement to process information in ways that would be impossible with classical systems, exploring multiple solutions simultaneously through quantum parallelism. Scientists have successfully created entanglement between particles separated by hundreds of kilometers. Using satellites to beam entangled photons across the vast experiments aren't just technologicalness of space. These achievements, they're profound investigations, successful demonstration into the nature of reality itself. Each of long-distance entanglement reinforces our understanding that the quantum world operates by principles that seem magical from our classical perspective. The delicate nature of entanglement makes it both powerful and fragile. These quantum connections are easily disrupted by interactions with the environment. Stray photons, thermal vibrations, magnetic fields, even the slightest disturbance can cause entangled particles to lose their correlation and become separate entities once again. This process, called decoherence, is why we don't observe quantum effects in our everyday lives. The warm, noisy environment around us constantly destroys quantum coherence, leaving behind the stable, classical world we experience. Yet perhaps the most profound aspect of entanglement lies not in its practical applications, but in what it reveals about the nature of existence itself. It suggests that separation, the quantum level, there might be an illusion, that a universe is far more interconnected than ours. When your senses suggest look up at the night sky, that your eyes from photons entering distant stars might carry with them quantum correlations. that link you to those far-off suns in ways that transcend space and time. This quantum connectedness doesn't require belief or faith. It's been verified through countless experiments and forms the foundation for emerging technologies. It's woven into the mathematical structure of reality itself, a feature of the universe as fundamental as gravity or electromagnetism. Every interaction between particles creates the potential for entanglement, meaning that quantum correlations are constantly forming and dissolving throughout the cosmos. As you rest tonight, consider that the atoms in your body were once forged in the hearts of ancient stars, and some of those atoms might still carry quantum memories of their stellar origins. The oxygen you breathe, the calcium in your bones, the iron in your blood, all were created through nuclear processes that relied on quantum mechanics. In a very real sense, you were made of stardust held together by quantum forces, a temporary arrangement of matter and energy that somehow gives rise to consciousness and wonder. The story of entanglement reminds us that reality is far richer and more mysterious than our everyday experience suggests. Beneath the familiar world of separate objects and clear boundaries lies a realm of infinite possibility and connection. This isn't mysticism or wishful thinking. It's the mathematical heart of quantum, through experiment and H-physics, verifying by technology. In our next gentle exploration, we'll discover how these quantum mysteries manifest in the biological world around us, where life itself might depend on quantum effects to achieve its remarkable efficiency and complexity. We'll see how evolution might have learned to harness the strange rules of quantum mechanics, creating biological systems that operate on the edge between the classical and quantum worlds. For now, drift peacefully, knowing that you exist in a universe where connection transcends distance, where particles dance together across the vastness of space, and where the deepest truths about reality continue to unfold like flowers blooming in the garden of human understanding. The quantum realm whispers its secrets to those patient enough to listen, revealing a cosmos far more wonderful and interconnected than we ever dared imagine. Tonight we venture into one of the most extraordinary frontiers of science, where the mysterious to dance principles of quantum mechanics begin with the processes of life itself. Here, in this gentle twilight between disciplines, we discover that the strange quantum effects we've been exploring may not be confined to steer abstract mathematical equations, our laboratories, or they might be quietly orchestrating some of the most beautiful phenomena in the natural world around us. Picture a robin preparing for its autumn migration, a journey that will take it thousands does this small creature navigate with of miles across remarkable precision. How continents with such accuracy across vast landscapes, through storms and changeangeously seen. For arrive at destinations whether, to it has never cont centuries, we've known that many animals possess compass, but some form of internal. The mechanism behind this navigation remained one of biology's most intriguing puzzles. Recent research suggests that the answer might lie in quantum entanglement occurring within the bird's very eyes. Deep within specialized proteins called cryptochromes, pairs of electrons may become quantum entangled when struck by light. These entangled electrons then interact with Earth's magnetic field in ways that depend on the bird's orientation, creating subtle chemical changes that the bird's nervous system can detect. The robin, in essence, might see magnetic fields as patterns of light and shadow overlaying its visual world, a quantum compass that guides its epic journeys. This isn't science fiction or wishful speculation that quantum entanglement can indeed persist in biological systems under. Laboratory experiments have shown certain conditions surviving far longer than many scientists thought possible in the warm, wet-sea environment of living. Noents within the bust extreme isolation in our laboratories somehow maintain their cohere cells. The delicate quantum states that require the greenling molecular machinery of life. Consider leaf rustling outside your window, a seemingly simple structure that performs one of the most important processes on Earth. Photosynthesis captures sunlight and transforms it into chemical energy with an efficiency that surpasses our best artificial systems. Plants convert nearly every photon that strikes their chlorophyll molecules into useful energy, achieving this remarkable feat through a process that classical physics struggles to fully explain. The secret appears to lie in quantum coherence. When a photon strikes a chlorophyll molecule, it creates what scientists call a packet of energy that must excite on, travel through the plant's molecular architecture to reach the reaction center where photosynthesis occurs. In a classical system, this energy through a process of trial energy appears to explore would hop randomly from molecule to molecule, losing efficiency and error. But quantum mechanics offers a more elegant solution. The multiple pathways simultaneously, existing in superposition as it samples different routes through the photosynthetic complex. Like a quantum ghost, it can test every possible path, selecting the most efficient route to, at once, automatically its destination. This quantum effect to achieve their remarkable efficiency by known as coherence allows plants essentially cheating the classical rules of energy transfer. The researchers propose that quantum effects might play implications stretch far beyond individual organisms, some crucial roles in processes as diverse as enzyme function, DNA replication, and even the emergence of consciousness itself, feigned. Instead of existing boundary between the quantum and classical worlds, may not in separate realms, these be as sharp as we once imaged together in ways that give rise to the complexity understanding of life's relationship. Two descriptions of reality might blend and beauty of living systems. This quantum biology challenges our traditional with physics. We've long assumed that biological systems operate primarily according to classical mechanics, it seems, has chemistry. But nature, with quantum effects relegated to the underlying discovered ways to maintain and exploit quantum phenomena, even offers another fascinating example. Traditional theories suggest that we detect odors through a lock-and-key mechanism, where molecules, the human in the chaotic environment of living cells, sense of smell fit into receptors based on their shape. But this explanation has always had puzzling gaps. Molecules with similar shapes sometimes can produce identical scents and smell completely different, while molecules with different structures, noses, might be quantum devices. Alternative theory proposes that our vibrational frequencies. According to this idea, detecting not just the shape of molecules, but their vids to a receptor when an odor molecule knows, electrons might tunnel through the molecule in a process that depends on how olfactory system to distinguish between molecules, Elling probabilities, allowing the molecule vibrates. Different vibrational patterns would create different turn aroma of fresh coffee. Quantum, you smell a flower or detect thed mean that every time based on their quantum mechanical properties. This would tunneling events are occurring in your nasal passages of nature's most elegant. Your sense of smell might be one quantum of electron, the strange properties sensors, capable of detecting molecular vibrations through earlier. Even tunneling that we explore more intriguingly, some scientists speculate that quantum effects might contribute to the phenomenon of consciousness itself. The microtubules within neurons, the cell's structural scaffolding, might maintain quantum coherence long enough neural processing. This to influence controversial idea suggests that the strange properties of super from the electrical activity of the roles in how thoughts emerge position and entanglement could play computation, maybe awareness itself odd possibility, perhaps consciousness brain. While these theories remain highly isn't simply an emergent property of complex classical speculative, they hint at a profound still in its infancy, with ICEs from the intersection of classical more questions than answers, many creating a form of information processing that transcends purely neural networks and quantum mechanical processes. Classical description. The study of quantum biology is proposed quantum effects in living systems remain controversial, requiring more research to establish their reality. Life has indeed and significance. But the evidence continues to accumulate that found ways to harness quantum phenomena for biological advantage. reveals nature as this research and even more sophisticated imagined. Over billions of years of to have discovered quantum engineer than we previously evolution, living systems appear solutions to biological challenges, developing molecular machines that operate on principles we're only beginning to understand. The warm, noisy environment that we thought would destroy quantum effects might actually provide the perfect conditions for certain types of quantum processes to flourish. These discoveries also suggest new directions for technology. If evolution has learned to maintain quantum coherence in biological systems, perhaps we can apply quantum devices. Nature, these lessons to create more robust, to build quantum computers that operate at room, might teach us how temperature, quantum sensors with unprecedented sensitivity, or energy harvesting systems that rival photosynthetic efficiency. The intersection of quantum physics and biology opens windows the relationship between mind and matter. How does consciousness emerge from into questions that touch the very essence of existence? What is physical processes? Could quantum effects explain phenomena like intuition, creativity, or the subjective experience of being alive? These aren't merely academic questions. They probe being in a quantum universe. As the deepest mysteries of life, we might discover that the it means to be a conscious. We uncover the quantum dimension's boundary between observer and observed, between mind and world, is far more fluid. Quantum nature of biological processes also provides a new perspective on our connection than our classical intuitions suggest. To the cosmos. The same quantum fields that govern the behavior of particles in distant dances within your cells. Galaxies also orchestrate the molecular. The uncertainty principle that shapes atomic interactions also influences the chemical reactions that sustain your thoughts and dreams. In this not separate view, you from the quantum universe, but intimately woven into its fabric. Every breath you take involves quantum processes. Every heartbeat depends on quantum tunneling in the ion channels of your cardiac cells. Every thought might emerge from quantum computations occurring in the neural networks of your brain. This quantum cosmic symphony, where the perspective on life invites us to see ourselves as part of a grand, strange rules of quantum mechanics, compose, beauty, and wonder. We melodies that somehow give rise to awareness are not mere observers of the quantum world, but active participants in its ongoing creation. Conscious expressions of the universe know itself. As we prepares capacity to explore even deeper quantum mysteries in our next journey together, rest in the knowledge that you are a remarkable quantum phenomenon, a temporary arrangement of matter and energy that has own existence. The same forces somehow learn to contemplate its, connecting you to the deepest structures that guide migrating birds and power photosynthetic reactions also flow through your being peacefully tonight. Knowing that you're the gentle border dreams themselves might of reality in ways both subtle and profound. Sleepland, between waking and sleeping, between participates in the cosmic dance of possibility, emerge from quantum processes, defines the quantum universe. In that your consciousness, an actuality that classical and quantum, between known and unknown, the mysteries of existence continue to unfold there. Secrets to those with eyes to see and hearts to wonder. As quantum tapestry, we drift deeper into this. We encounter one of the most profound puzzles in all of physics. A mystery that has puzzled scientists for nearly a century and continues to whisper its secrets in of what happens when the laboratories around the world. It's the question quantum realm meets the classical world we know and love. Imagine standing at the shore where ocean waves meet the sand. The waves roll in with fluid grace, each one unique, yet following predictable patterns. But as they crash against the beach, that smooth, wave-like motion suddenly transforms into something entirely different. Scattered droplets and foam that behave like individual particles. This transition from wave to particle, from fluid to discrete, mirrors one of the deepest mysteries in quantum physics. In the quantum world, particles exist in superposition, embodying all possible states simultaneously until the moment of measurement. But in our everyday experience, we never encounter objects that are simultaneously here and there, spinning up and down, or moving in multiple directions at once. Somehow, the fuzzy quantum possibilities crystallize into definite classical outcomes. The question that has haunted physicists for generations is simply, does the transition this? How happen, and why? The answer lies in a gentle but relentless process called decoherence, a phenomenon as subtle as morning ving in mist dizzelight. Every quantum sun-exists system in delicate isolation, maintaining its superposition state's balanced dancer like a perfectly frozen in mid-leap. But the moment that system interacts with its environment, even in the tiniest way, the dance begins to falter. Consider an electron in superposition, existing in multiple locations simultaneously. In the perfect vacuum of space, far from any disturbance, this electron could maintain its quantum coherence indefinitely. But bring it closer to Earth, into the warm bath of thermal radiation, stray electromagnetic fields, and wandering particles that fill even the emptiest spaces, and something remarkable happens. The electron begins to entangle with its surroundings. Each photon that brushes against the electron, each magnetic field flux, creates suation that touches it tiny angle. Enterments between the particle and the environment. These are the dramatic entanglements we explored earlier, where particles maintain nations across vast distances, instead clear correlled. They're countless microscopic connections that gradually blur the electron's quantum coherence. Think of it like trying to have a whisper in a crowded restaurant. Initially, you and your companion can hear each other clearly, maintaining your private dialogue. But as the ambient noise increases, as more conversations swirl around you, your words begin to blend with the general chatter. Eventually, your private exchange becomes indistinguishable from the background noise, lost in the acoustic environment surrounding you. This is decoherence in action, the quantum system's private superposition becoming entangled with the countless degrees of freedom in its environment until the coherent quantum behavior dissolves into classical uncertainty. The superposition doesn't disappear entirely, it becomes so thoroughly scrambled with environmental interactions that we can no longer detect its quantum nature. The speed of this decoherence depends on the size and complexity of the quantum system and its coupling to the environment. For microscopic particles in carefully controlled laboratory conditions, coherence can persist for microseconds or even milliseconds, long enough to observe and manipulate quantum effects. But for larger objects in warmer, noisier environments, decoherence happens almost instantaneously. This explains why you never find your coffee cup in a superposition of being simultaneously on the table and in the cupboard. The cup consists of countless atoms, each one constantly interacting with air molecules, thermal radiation, and electromagnetic fields. Within an unimaginably brief moment, any quantum coherence the cup might have possessed becomes entangled with the environment, leaving behind the definite classical object you observe. Yet decoherence doesn't solve every mystery of quantum mechanics. It explains why we don't see quantum effects in everyday life, but it doesn't fully address the deeper puzzle, known outcomes rather than maintaining question of why measurements as the measurement problem remains one of seem to produce specific interpretation of quantum mechanics. Some, the quantum superposition, indefinitely. This, the most contentious issues in the physicists embrace the Copenhagen interpretation, which simply accepts that measurement produces definite outcomes without worrying too much about the underlying mechanism. Others prefer the many worlds interpretation, suggesting that all possible measurement outcomes actually occur, branching into parallel universes that we cannot access. Still function spontaneously collapses. According, others propose objective collapse theories, where the wave to yet unknown physical processes. Each on the boundary between quantum and classical real interpretation offers its own perspectives. But regardless of which philosophical stance you preferenate the microsc, the practical opic world, while quantum effects dom the same. Consequences remain. Classical physics describes the macroscopic realm we inhabit, with decoherence serving as the bridge between these two descriptions of reality. This boundary isn't sharp like a gradient, with quantum effects gradually. Instead, it's more or absolute fading as systems become larger, warmer, and more connected to their environment. Some systems, like the biological quantum processes we explored earlier, operate boundary, maintaining just enough quantum coherence to gain right at this advantages, while remaining robust enough to function noisy environment of living cells. Modern in the quantum technologies dance along boundary, using sophisticate this same isolation techniques to preserve quantum coherence long enough to perform useful computations or create secure communications. Quantum computers must be cooled to temperatures colder than outer space and shielded from electromagnetic interference to maintain the delicate superpositions that give them their computational power. It's a constant battle against decoherence, using the tools of classical engineering to protect quantum phenomena long enough to harness their potential. But perhaps the most beautiful aspect of decoherence is how it reveals the interconnected nature of reality. No quantum system truly exists in isolation. Every particle, every atom, every molecule is constantly exchanging information with its surroundings, creating a vast web of correlations that extends throughout the universe. What we perceive as classical objects are actually stable patterns in this quantum information network, temporary arrangements that maintain their form through the continuous dance of decoherence and suggest that the classical world isn't recoherence. This perspective is separate from the quantum realm, but emerges from it, like waves forming on the surface of a deep ocean. The solid chair supporting you, the warm air surrounding you, the gentle light illuminating your space, all arise from quantum processes that have decoherent into stable classical patterns, while remaining fundamentally quantum in nature. As we prepare to explore even stranger territories in our quantum journey, take comfort in this view of reality as a seamless whole, where classical and quantum descriptions complement rather than contradict each other. The boundary between them isn't a wall, but a gentle transition, like the way daylight gradually gives way to twilight, each phase beautiful and essential in its own way. In our next gentle exploration, we'll venture into one of the most mind-bending territories in all of physics, where the very act of choosing what to observe seems to influence not just the present, but the past itself. We'll discover experiments so strange that they challenge our most basic assumptions about the nature of time and causality, revealing a universe where the future might help determine the past in ways that stretch our understanding to its very limits. For now, rest peacefully in the knowledge that you exist at the beautiful intersection of quantum possibility and classical certainty, where the microscopic gives opic dance of probability rise to the stable, predictable world that cradles your dreams. The boundary between quantum and classical is not a barrier but a bridge, connecting the mysterious realm of quantum mechanics to the familiar world of everyday experience in ways both subtle and profound. Sleep gently washes over us as we approach one of the most bewildering chapters in our quantum story, where the simple act of deciding what to observe appears to reach backward through time itself, reshaping events that have already occurred. These are experiments so delicate and profound that they seem to mock our everyday understanding of cause and effect, revealing a universe where the arrow of time itself becomes as uncertain as a quantum particle in superposition. Picture yourself standing before two doorways, each leading down a different corridor. In the classical world, once you choose add walk through path and one door, your choice is final. The corridor you didn't remains take unexplored, a road not taken that exists only as a memory of possibility. But in the quantum realm, fed in ways that were rules bend make Lewis Carroll smile with recognition, scientists have devised experiments where particles are sent toward barriers containing two openings, much like our corridors. In the standard version of this setup, when particles pass through both openings simultaneously, they create the beautiful interference patterns we've come to expect from quantum waves. But here's where the story takes a turn toward the extraordinary. Researchers can choose whether to measure which path the particle took, and they can make this choice after the particle has already passed through the openings, but before it reaches the final detector. What they discovered challenges everything we thought we knew about the relationship between past, present, and future. When the scientists decide to measure the path after the particle has supposedly its route already chosen, the interference pattern vanishes, just as if the particle had been forced to pick a single path from the very beginning. It's as though the particle somehow knew about the future measurement and adjusted its behavior accordingly, traveling through only one opening instead of both. The implications whisper through the corridors of physics, like a secret too strange to believe. The particle's past behavior appears to be influenced by decisions that haven't been made yet. Time, it seems, doesn't flow in the simple, linear fashion our intuition suggests. Instead, the quantum world operates in a more fluid temporality where future choices can ripple backward to influence past events. This phenomenon becomes even more mysterious in experiments known as quantum erasers. Imagine marking the particles as they pass through each opening, like giving them tiny name which tags that identify path they took. This is the interference labeling destruction pattern, forcing the particles to behave like classical objects with definite trajectories. But then comes twist. Scientists, the magical, can erase this path information after the particle has been detected, removing the name tags after the fact. When they do this, something extraordinary happens. The interference pattern returns, appearing retroactively as though there all along. The particles had begin behaving like waves again, not just from the moment of erasure forward, but extending backward to influence their original behavior. It's as if reality itself is being rewritten, with the past adjust aren't philosophicaling to accommodate present choices. These thought experiments or science fiction scenarios, they're real phenomena measured in laboratories around the world with exquisite precision. The universe appears to operate according to principles that transcend our classical notions of temporal order. Events don't simply unfold from past to future in a neat causal chain. Instead, the quantum realm reveals a more complex tapestry where past, present, and future are interwoven in ways that challenge our deepest assumptions about the nature of reality. One way to understand this temporal strangeness is to think of quantum systems as existing in a state of temporal superposition, much like their spatial counterparts. Just as a particle can exist in multiple locations simultaneously, perhaps quantum events can exist in multiple temporal states until the moment of observation crystallizes them into a definite sequence. The future measurement doesn't send a signal backward through time in any conventional sense. Rather, it helps determine which version of the past becomes actualized in our experience. This interpretation suggests that the quantum world operates according to what physicists call a block universe perspective, where all moments of time exist simultaneously in a four-dimensional structure. From this view, our experience of time as flowing from past to future is an illusion created by our limited perspective. The quantum delayed choice experiments might be giving us glimpses of this deeper temporal reality, where causality operates in ways more subtle and complex than our everyday experience suggests. The philosophical implications ripple outward like waves in still water. If the future can influence the past, what does this mean for free will? Are our choices truly free? Or are they part of a cosmic choreography that extends across time? Does consciousness play a special role in crystallizing quantum possibilities into definite realities? These questions probe the deepest mysteries of existence, touching on issues that have puzzled philosophers and scientists for centuries. Yet perhaps the most profound lesson from these temporal quantum puzzles is one of humility. They remind us that our intuitions about time, nature of reality, our shape causality, and led by our limited experience, operates according to principles far at the macroscopic scale. the universe more subtle and beautiful than our everyday logic suggests. What appears impossible from our classical perspective might simply reflect the limitations of our imagination rather than the boundaries of what nature allows. Modern quantum technologies are beginning to harness these temporal quantum effects in remarkable ways. Quantum computers paths simultaneously, including paths that seem to flow backward through logical sequences, can explore multiple computational. Some researchers speculate that quantum biology might utilize these temporal effects, allowing living systems to sample future possibilities and optimize their present behavior accordingly. Choice experiments also shed the delayed new light on the nature of observation itself. They suggest that the act of measurement isn't simply revealing pre-existing properties, but actively participating in the creation of reality. The observer and the observed are partners in an ongoing dance, where the distinction between subject and object becomes as fluid as the boundary between past and future. This perspective transforms our understanding of scientific inquiry itself. We're not passive observers studying an objective reality that exists independently of our investigation. Instead, we're active participants in the universe's ongoing process of self-discovery. Every quantum measurement is a moment of cosmic creativity, where possibilities crystallize into actualities through the intimate partnership between observer and observed. As we drift deeper into these temporal mysteries, we begin to see hints of an even grander vision. Perhaps the entire universe operates as a vast quantum system, with its history not fixed in stone, but continuously being written and rewritten through the countless measurements and observations occurring throughout space and time. The past might not be as immutable as we imagine, while the future might be more influential than we dream. The quantum eraser experiments reveal reality as a collaborative artwork, painted by the interplay between possibility and actuality across the dimensions of space and time. We're not just watching this cosmic creation unfold, we're helping to paint it, one observation at a time. Every choice to look or not to look, every decision about what to measure and when, contributes to the ongoing masterpiece of existence. In this view, consciousness might play a special role not as a passive observer of reality, but as an active participant in its creation. The delayed choice experiments hint that awareness itself might be woven into the fundamental structure of the universe, helping to determine which possibilities become actualized through the mysterious process we call measurement. Tonight, as you rest in the gentle twilight between waking and sleeping, consider that you exist in a universe where time itself is quantum, where the future whispers to the past in languages we're only beginning to learn. The moments of your life aren't simply flowing from yesterday through today toward tomorrow. They're part of a more complex temporal symphony, where each note influences not only what comes after, but also what came before, creating harmonies that span the breadth of existence itself. These temporal quantum mysteries remind us that reality is far richer and more interconnected than our classical intuitions suggest. The universe doesn't simply unfold according to predetermined laws. It participates in its own creation, continuously writing and rewriting its story through the delicate interplay between observation and possibility. We're not just characters in this cosmic narrative. We're co-authors, helping to determine which of the infinite possible stories becomes the one we call reality. Sleep peacefully, knowing that you're part of this grand temporal tapestry, where every moment connects to every other moment in ways both subtle and profound. The quantum realm operates by principles that transcend our everyday understanding of time and causality, revealing a universe where the very act of observation participates in the ongoing creation of existence itself. In dreams, perhaps, we glimpse something of this deeper temporal reality, where past and future dance together in the eternal now of quantum possibility. We drift further into this quantum dreamscape, where we encounter one of the most beautiful and mysterious aspects of our strange universe, the gentle dance of randomness and order that weaves through the very fabric of reality itself. Tonight, we explore how the cosmos plays dice with existence, yet somehow takes our breath away. Pictured precise that they take patterns so elegant in yourself sitting by a quiet stream in the early morning, watching autumn leaves fall from the trees above. Each leaf follows its own unique spiraling in ways that seem completely tumbling, unpredictable. You random and UNP can't possibly know where any individual leaf will land. Yet somehow, over time, they create beautiful patterns along the water's edge, natural arrangements that speak of deeper harmonies hidden beneath the apparent chaos. This is the essence of quantum randomness, a fundamental uncertainty that lies at the heart of all existence. When we peer into the quantum realm, we discover that nature doesn't follow the rigid, clockwork precision that, instead, it operates on probability our classical intuition expects, on chance, on the roll of cosmic dice that determines the fate of every moment of quantum particle, every interaction reality. Albert Einstein famously struggled with this idea, could not believe the declaring that his universe was governed by chance. He imagined there must be hidden clockwork beneath the quantum uncertainty, secret variables that predetermined every outcome, even if we couldn't see them. But decades of careful experiments have shown that Einstein's hopes for a deterministic universe were beautifully wrong. The cosmos really does embrace uncertainty as a fundamental feature, not a flaw to be corrected. This quantum randomness isn't chaos in the destructive sense. Like cosmic jazz, where individual notes may be unpredictable, but they come together to create melodies of breathtaking beauty and mathematical precision. When physicists calculate the probabilities of quantum events, they find agreement with experimental accurate to more than results that is 10 decimal places. The uncertainty is structured, elegant, following laws as precise as any in classical physics. Think die. The outcome of rolling a single of any individual roll is genuinely random, impossible to predict with certainty, but roll that die 1,000,000 times and patterns emerge. The statistics become reliable, predictable, beautiful in their regularity. This is how quantum mechanics works on the grandest scales. Individual quantum events are random, but the statistical behavior of countless particles creates the stable, predictable world we inhabit. This interplay between randomness and order extends throughout the natural world in ways both subtle and profound. The mutations that drive evolution occur through quantum processes in DNA molecules, random changes that occasionally create new possibilities for life to explore. Without this quantum randomness, evolution would grind to a halt, unable to generate the variety and complexity that fills our living world with the stars' such magnificent diversity. Even themselves depend on quantum uncertainty for their existence. Deep within stellar cores, hydrogen nuclei overcome their electrical repulsion through quantum tunneling, a process that relies on the probable of quantum mechanics. Without istic nature fundamental randomness, the nuclear this furnaces that light the cosmos couldn't ignite, and the universe would remain cold and dark, devoid of the energy needed for complexity and life. The quantum vacuum, that supposedly empty space between particles, seethes with random fluctuations that pop virtual particles in and out of existence in fleeting moments too brief to observe directly. These vacuum fluctuations aren't just mathematical abstractions. They have measurable effects on the behavior of atoms and the structure of space-time itself, contributing to phenomena from the stability of matter to the expansion of the universe. Yet perhaps the most profound aspect of quantum randomness is how it challenges our deepest assumptions about knowledge and reality. In the classical world, we imagine that perfect knowledge should be possible in principle. If we could measure everything precisely enough, we should be able to predict the future with complete accuracy. But quantum mechanics reveals this dream to be fundamentally impossible, not because of limitations in our instruments or methods, but because the universe, rather than certainty, This in itself operates on probability cause for despair, but for wonder. Quantum uncertainty creates space for genuine novelty, for outcomes that couldn't be predicted from initial conditions. It means the universe is creative in the deepest sense, continuously generating new possibilities that couldn't have been foreseen even with perfect knowledge of the past. Every quantum measurement is a moment of cosmic creativity, where one possibility crystallizes out of the quantum foam while others fade back into potential. The randomness also has a peculiar beauty in how it preserves the mystery of existence while still allowing for scientific understanding. We can calculate probabilities with extraordinary precision, predict statistical outcomes with remarkable accuracy, and build technologies that harness quantum effects with incredible sophistication. Yet the individual quantum events themselves remain fundamentally unpredictable, maintaining an element of surprise that keeps the universe from becoming a mechanical automaton. This quantum uncertainty might even be essential for consciousness itself. Some researchers speculate that the random quantum events in neural microtubules could provide the spark of creativity and free will that distinguishes conscious beings from purely mechanical systems. While these ideas remain highly speculative, they suggest that the fundamental randomness of quantum mechanics might be intimately connected to the deepest mysteries of awareness and choice. The dance between randomness and order in quantum mechanics also offers a different perspective on meaning and purpose. Rather than seeking a universe where everything is predetermined by rigid laws, we find ourselves in a cosmos that balances structure with surprise, predictability with possibility. This quantum universe is neither purely ordered nor purely chaotic, but something more interesting. A realm where patterns emerge from uncertainty, play of chance and necessity, where beauty arises from the As we contemplate these quantum mysteries, we might find comfort in the realization that uncertainty, enemy of knowledge, but its partner, isn't the use that some questions don't have definite. The quantum realm teaches ignore answers not because but because the questions themselves probe beyond the boundaries of what can be definitely known. This space for wonder isn't a limitation but a feature, creating for surprise, for the ongoing adventure, modern of discovery. Quantum technologies embrace them, fighting against this uncertainty rather it. Quantum cryptography uses the random nature of quantum measurements to create perfectly channels. Quantum random secure communication number generators harness quantum uncertainty to produce truly unpredictable sequences for security to scientific ranging from computer application simulations. We're learning to dance with quantum randomite. Sleep gently tonight, knowing that you exist within a universe far more wondrous than our ancestors ever dared imagine. We've journeyed together through realms where particles dance in superposition, where observation creates reality, and where the very fabric of space and time whispers secrets of quantum entanglement. From the gentle uncertainty that keeps atoms stable to the biological quantum compasses that guide migrating birds, we've discovered a cosmos where mystery and precision intertwine like lovers in an eternal waltz. Rest peacefully in this quantum embrace, where even your dreams might emerge from the same probabilistic poetry that governs stars and synchronizes distant particles across the vastness of space.